Okay, so how do atoms bond, or what does it mean when when more than one atom bonds together to form molecules? There are three types of bonds: covalent bonds, ionic bonds, hydrogen bonds. Covalent bonds and ionic bonds are bonds that occur between atoms. I'm trying to get a pen here. Oh, maybe I have to be in slideshow mode. There we go. Okay, so covalent bonds and ionic bonds, they form between atoms that makes the molecules. So covalent bond would be a bond between at least two atoms that makes a molecule. Ionic bond, the same thing, a type of bond between two atoms that makes a molecule. Hydrogen bonds is different. Hydrogen bonds is between the one atom in one molecule and a different atom in another molecule. So hydrogen bonds hold a molecule to another molecule. So covalent bonds would be within one molecule. Ionic bonds would be within one molecule. But hydrogen bonds are between two different molecules being attracted to each other in a way. But whatever the type of chemical bond, it's the attractive force that brings things together, either atoms or, well, it is atoms, but atoms in different molecules attract in a hydrogen bond. So we're going to go through each one of them, but the point of all of these things is, first of all, this is how in our hierarchy, a biological organization, a bond is what takes different atoms and forms them into molecules. And so that goes from that first level to the next level. And it is ultimately the way that each atom attempts to fill its valence shell in some way. That's the way that atoms tend to react, is to fill their valence shell. And when atoms form bonds, especially covalent or ionic bonds, they lose their physical characteristics of the element that they were, and they take on sort of different characteristics. In other words, like sodium and chloride is salt, like the salt you eat. But sodium by itself, when it's just a pure element, when it's just the atoms of sodium, is actually a soft metal. You would never eat it. And chlorine by itself, you would never eat it. It's a chemical that is very antibacterial, antimicrobial. It's in bleach. You put tablets of chlorine in your pool to keep it clean. You would never eat it. So you've got this metal that you would never eat. You've got this chemical that you would never eat. But when they form a bond, it's salt, which has a lot of uses, but you can eat it. So it's something to keep in mind, is that when atoms form bonds, they take on some new characteristics, I guess you could say it. All right, so the point, though, is that the atoms are trying to fill their valence shells individually. If filling a valence shell is impossible with one bond, it will form more than one bond. All right. Sometimes it's easier for an atom to fill a valence shell by emptying. Maybe it has one electron in its valence shell. Sometimes it's easier for it to give that electron away. And remember, if the shell doesn't have any electrons, it disappears, such that the shell before it, the previous shell, is then the valence shell, which is full. So that's something that's pretty common as well. Okay, a covalent bond is when a pair of electrons, valence electrons, is shared. So for example, hydrogen has one valence electron and then one valence electron from oxygen, which oxygen has 6 valence electrons, but one of the valence electrons from oxygen, this would be what we would call a pair of electrons that is shared. So the hydrogen shares its electron here, so you can see they kind of overlap their shells, and the oxygen shares its one electron, and so this is the pair of shared electrons. So we usually draw it in just a little line, just a little short line. Between the O and the H, there's a little short line. That means there's a pair of shared electrons. Now over here you have another pair of shared electrons. So that's another bond. Oops. I'm just trying to highlight this. All right. Now when the orbitals are overlapping like this, when the electron shells are overlapping like this, the hydrogen sort of is believing that it has 2 electrons in its valence shell, and this hydrogen over here thinks it has 2 electrons in its valence shell, and the oxygen thinks it has 8 electrons in its valence shell. It's sort of, everybody is sort of being fooled, because in reality, you know, each of them can't have a full shell without adding electrons from elsewhere. But each of them, because they're sharing electrons, each of them believes it has a full shell, and this is the most stable situation. So all 3 of these atoms will stay connected like this and maintain the illusion, I call it the illusion, of having a full shell. And it's very hard. You can break apart a water molecule, but it takes a lot of energy to break apart, because these atoms are so stable when they're in this arrangement that they will hold very tightly. A covalent bond is a very strong bond. It's by far the strongest bond. So it's a shared electrons. You can have, for example, 2 oxygens can share 2 pairs of electrons. So let's say they share these 2 and then they share these 2. So if you kind of redraw it this way, you'd have a bond made up of these 2 electrons and a second bond. That's called a double bond. And it would be drawn like this in a shorthand. There is such a thing as a triple bond, not for oxygen. Nitrogen can, let me think. No, nitrogen would not form a triple bond. Carbon to carbon can be a triple bond. It's pretty odd though. But in any case, double bond is reasonably common. So when you look at this, for example, this oxygen nucleus here, when it looks at its valence shell, it gets to count all of the electrons, even the ones that are shared. So when you look at it, it thinks it has these 4 and then it counts those 4. So it thinks it has 8. This oxygen nucleus thinks it has 8. Now, does each of them separately have 8? No. They're sharing. There's 4 of them that are being counted on both, for both nuclei. But they believe that they each have a full shell, so they will stay together to maintain that illusion. It's kind of an interesting thing, but it's a very strong force. All right. We're not going to go too much into how to write the formulas. You probably have some familiarity with it. If there's a little subscript next to a symbol, H2 means 2 hydrogens, O2, 2 oxygens. H2O would be 2 hydrogens and an oxygen. And what's important there is that this formula here doesn't tell you what the arrangement is. You would have to kind of work it out based on how many valence electrons each of the components have. But we're only going to learn a few of these. Remember, we're going to focus on oxygen, hydrogen, carbon, and nitrogen. So you'll be able to make these, figure these things out pretty quickly. And here's methane. Methane is 4 bonds with 4 hydrogens. So this is called the Lewis dot structure. It just focuses on the shared electrons. And this is called the space filling model. It's trying to give you kind of a 3D image of what the molecule might actually look like. But you're not going to have to draw those. All right. So I think the most important thing that you could learn at this point is a few of the rules for the 4 elements. Oxygen always wants to make 2 bonds, 2 covalent bonds. Hydrogen wants to make 1. Each hydrogen needs to make 1. And nitrogen needs to make 3 bonds total. And carbon needs to make 4. So you memorize that. Oxygen wants to make 2 bonds. Hydrogen makes 1, nitrogen makes 3, carbon makes 4. And so when you look at something like methane, so you know this is the correct structure because carbon, you should be able to draw or find 4 bonds coming out of the carbon, which you do. And then each of the hydrogens has 1 bond coming off of it. So it checks out. Oxygen, like in water, oxygen has 2 bonds, so that's correct. And each of the hydrogens has 1 bond. So, you know, how many bonds are coming off of that symbol? It should always match up to these rules that I've laid out for you. Oxygen always has 2. Hydrogen only ever has 1, nitrogen has 3, and carbon has 4. So that's something you really have to memorize, or else, you know, it's not, you don't want to have to figure that out every time. Okay, so that's one of those things you just know. Now, with covalent bonds are strong. They're hard to break. Not impossible, but hard to break. It would take a lot of energy to break a covalent bond. But there's something else about them, and that's that not all covalent bonds are, I guess, what we call equal, or maybe I should say, some covalent bonds are, the electrons are shared evenly between the 2 partners that are sharing. And some covalent bonds, the sharing is not even. And we call this concept electronegativity. So atoms of different elements have a different affinity for electrons. Affinity is how much they want the electrons. And there's a rule for it. And here's another thing you just want to memorize. The 2 atoms out of these 4 that we're looking at, oxygen and nitrogen, have a very high affinity. That's oxygen and nitrogen have a very high affinity. They are highly electronegative. That means how much, that if I say they're highly electronegative, they have a very high affinity. They really want the electrons. Highly electronegative, high affinity, electronegative. Okay. Hydrogen and carbon are not that highly electronegative. So I'm going to say H and C. I ran out of room. H and C, not too electronegative. You know, they're moderate. I'm going to put not very electronegative. I'm not saying they don't want electrons, but not nearly as much. Not very electronegative. Now this is going to be good enough for us, these definitions. So you want to remember that the oxygen and the nitrogen are very electronegative. Sometimes I call it electron greedy. They really want those electrons. Some atoms like hydrogen and carbon, you know, they'll share them just nicely. They'll share very nicely. So if you have a bond, a covalent bond that forms between one atom that's very electronegative, oxygen or nitrogen, and one atom that's not so electronegative, like hydrogen and carbon, the greedy one will share the electrons more to itself. I say it kind of hogs them. It pulls them around itself more. So in theory, the electrons that are shared should be traveling around both nuclei. They should be traveling around, let's say you have an oxygen and a hydrogen with a a pair of electrons that are shared. Those two electrons should, if things were even, they should spend some time around the oxygen nucleus and some time around the hydrogen nucleus, and it should be even. But it's not, because the oxygen is more greedy, so it keeps those electrons more often around its own nucleus. And the nucleus of the hydrogen atom finds itself without any electrons a good amount of the time. And so what that does is, because the electronegative nucleus is pooling all the electrons more towards itself, what it means is that you get an uneven sharing of the electrons. That's what we usually call it. All right. Now, sometimes one of the atoms is so greedy it actually pulls the electron completely away from the other. And we usually use this example here. Carbon, oxygen, hydrogen, and nitrogen don't do this. But it's chlorine. Chlorine has 7 electrons in its valence shell. Sodium only has 1. So chlorine is very highly electronegative. It really wants to get that one more. It just needs one more. And so it will actually steal it from another compound. It turns out that sodium is very happy to give up its 1 electron. And so it's kind of a win-win. The chlorine can steal the electron from the sodium, and you can see it over here. It just completely takes it. This is not a sharing. This is a taking. And the sodium then, remember we said if a shell doesn't have anything in it, it disappears. And so what you really have in sodium is the second shell. The third shell is the valence shell initially, but it actually will disappear, and the second shell then becomes the valence shell, and the second shell is full. So both of them end up with a full valence shell. I kind of wish on this picture they took off. They should never draw an empty shell. It disappears, and then the one beneath it is now the valence shell for sodium. So in any case, what happens is the chlorine just wants the electron. But when it takes that electron, it now has 1 more electron than protons. So now it has a negative charge. We call that an ion, a charged atom. Neutral atoms we've talked about. Charged atoms are called ions. So now the chlorine is charged, and we call it chloride ion. The sodium atom now has 1 less electron than it should, and so it takes a positive charge. That's the sodium ion. Each of them is happy now, though, because they each now have a full valence shell. But one thing you'll remember probably is that opposites attract, and so now after the electron is completely transferred, stolen, if you will, or maybe given away, the 2 ions have opposite charges, so they stick to each other. They're stuck together. They're not sharing their electrons, but they're stuck together based on the electrical attraction of opposite charges. So it's an ionic bond. That's the attraction between them. It's electric. It's an electric bond. It's an electric charge. So ionic bonds are electric. But anyway, we call it ionic bond. The electrons are not shared, but the transfer of the electron creates opposite charges, which are then attracted to each other. So ionic compounds are typically things like salts. Most things are salts that have ionic bonds. For the atom that took a positive charge after the transfer, that's called the cation. I know it doesn't look like that's how you would pronounce it, but it is. A cation. They almost should have just made it 2 words, cation. It's kind of like the word cathode and anode. If you think about a battery, which is electrical, the cathode and the anode. The cation is the positive and the anion is the negative. So that's just some vocabulary for you. Okay, but let's go back to talking about the shared electrons. What happens when an oxygen is pooling more on the electrons in the covalent bond than the hydrogen? So they gave you this example here because it's classic. I mean, it's the one you should learn. The oxygen pulls more on the electrons, so the electrons spend more time around the oxygen nucleus and less time around the hydrogen. So the oxygen has what we call a partial negative charge. And that just means that more often than not, the electrons are on that side. The hydrogen has more often than not, has a shortage of electrons on its backside here. And so we call that a partial positive charge. Now still, the whole thing completely taken as a whole is neutral, not charged. But what we're saying is there's an unequal spread of electrons. The electrons are more on this side. The electrons are more on the oxygen side than on the hydrogen side of this molecule. And so we use this little delta. This is delta. It's a lowercase. It's almost like an S, but then you can continue and connect it. So it's like the Greek lowercase d. The uppercase delta looks like a triangle. The lowercase delta looks like almost like a lowercase letter d, or kind of an S that kind of hooks all the way around. But in any case, partial negative charge on the side of the molecule where the really electronegative atom is, and the less electronegative atom would be partial positive. Partial is the delta. So when there are two different ends of the molecule in terms of partial charge, we call that a polar covalent bond. So polar means there's kind of opposite ends. Like the North Pole and the South Pole have different magnetic or electrical. There's one that's positive and one that's negative. If you use a compass, it'll turn to the north. So it's based on this electrical thing. This partial electrical difference across the bond is called a polar bond. And there really aren't, like, an ionic bond is fully polar because you have a full positive charge on one atom and a full negative charge on the other atom. So I guess it makes sense to call it polar covalent. You also have nonpolar covalent. A nonpolar covalent bond would be where the two atoms that are in the bond, they're pulling equally on the electrons. So carbon and hydrogen are both not that electronegative, so they'll both pull equally on the electrons, and so it ends up being an equal distribution of electrons. There's not one end that has more electrons than the other. So we call that nonpolar. And if you have any two atoms that are the same, like oxygen to oxygen in a molecule, that's nonpolar because they're the same. Even though both of them are very electronegative, it's like playing tug of war with somebody who's exactly the same strength as you. It ends up evening out. There's neither one can pull more than the other. They'll pull equally. They'll both pull hard, but neither one will be able to overpower the other. So that would be an oxygen to oxygen bond would be nonpolar. Nonpolar. The only time you have a polar bond is if you have an oxygen to hydrogen, oxygen to carbon, or like here's oxygen to carbon, or nitrogen to hydrogen or nitrogen to carbon. There's one exception. This is the beast right here. Everything else follows the rules. Carbon dioxide is nonpolar. Oxygen in the air is nonpolar, but that one follows the rules. Why is this one nonpolar? Because the reason carbon dioxide is nonpolar, this bond would be a polar bond, and this bond would be a polar bond based on the rules I taught you, because carbon doesn't pull as hard as oxygen. But what happens in carbon dioxide is that the actual shape of the molecule is this. It's actually shaped like, it's like a 180-degree line, well, 180-degree angle What's 180? It's just a line, 180-degree line. You know what I mean. It's just like a line. So it's a very linear molecule. So the carbon's in the middle and the two oxygens are on either side, and it's a straight line. And what happens is both of the oxygens are pulling. So what you end up with is on one end of the molecule you have partial negative. On the other end you have partial negative. It's very symmetrical. And in the middle you have partial positive. But because of the linearity of it, it's nonpolar. We only look at the ends, and the ends are both partial negative, so there's not one that's different than the other. Pretend like you don't know that the middle is partial positive. So the two ends are partial negative, so it's not like one end is different than the other end. They're both the same, so it reacts like a nonpolar molecule. So oxygen in the air is nonpolar. Carbon dioxide, strangely, is nonpolar. Now let's look at this one. Let's look at this one here. Carbon to hydrogen, carbon to hydrogen, carbon to hydrogen, carbon to hydrogen. All carbon to hydrogen bonds are nonpolar. So if all the bonds are nonpolar, then the whole molecule is nonpolar. That one's not an exception. And then water. Water is bent. If it was linear, like carbon dioxide, it would be nonpolar, but it's bent. So you'll just learn that the shape of water is actually this shape. It actually makes kind of this V shape, I guess you could say. All right. Usually if we were in class, I would do, I call it my cheerleading. I would say, okay, oxygen is here, and this is hydrogen, and this is hydrogen. You can't even see my arms right now. And I hold them sort of at an angle in front of me, but it's not a linear molecule. It has like a shape to it. And because of that, you clearly have on the, I guess you could call it the back end of the oxygen, that's where all the electrons would be. That's the partial negative side. And then you sort of have on the front side two positive, partial positives. So that's very polar. All right. So as a rule, if the bonds are polar in between the atoms, then the whole molecule is polar. If the bonds are nonpolar, then the whole molecule is nonpolar. What if you have a molecule that has some polar bonds and some nonpolar bonds? That will happen, but we're not going there yet. So don't panic yet. Okay, let's just learn the small ones, these ones that they either go one way or the other. But the one that you have to know and really just memorize is carbon dioxide. Even though it has two polar bonds, the whole molecule will be nonpolar. So that's weird. That one's a special one. They made a point to put it here. Okay. Carbon dioxide. And then oxygen, the reason I mention oxygen, it's just a nonpolar. It's nothing unusual about that. But we are going to talk about oxygen in the air, carbon dioxide in the air. I think you know it has something to do with respiration. And so knowing that those molecules are both nonpolar actually explains why they interact in a certain way that they do. So right now we're just needling down on what their chemical property is. And then later we're going to use that. Remember, we're laying down those foundations just like you memorized all of your math facts before you went to calculus. All right. So a lot of definitions and vocabulary that are in here. All right. So I think I went through this. This is another way of drawing water here. This would be the space filling model. Actually, it's kind of a space filling model, and then it has kind of a Bohr model laid over it, but whatever. Here's oxygen and two hydrogens, so you can see that shape, that kind of V shape of the water molecule. All right. The oxygen, because it's very electronegative, it will pull all the electrons, and the electrons will spend a lot more time sort of on this back end of the molecule and a lot less time. There's, I guess, a shortage of electrons most of the time on the front end of the molecule, or maybe there's two front ends of the molecule. And so that's where we call it the partial positive ends and the partial negative side. All right. So they're saying slight positive, I'm saying partial positive. It means the same thing. All right. Now, like I said, anything that has, if you have two molecules of the same type, excuse me, scratch that, two atoms of the same type in a bond, that's always going to be nonpolar because they both will pool evenly on the electrons. So if you have nitrogen to nitrogen, there's no difference in strength on either end of the bond. If you think of each of these atoms pooling like a tug of war, and the bond, I guess, is kind of like the rope, then neither one is going to win because they're the same. So that's nonpolar. If you have oxygen to oxygen, that's going to be nonpolar. If you have carbon to carbon, nonpolar. If you have hydrogen to hydrogen, nonpolar. So nonpolar is when they're the same, or if they have the same electronegativity. So if you have a nitrogen bound to an oxygen, which almost never happens, but let's say you had that, that would be nonpolar because they're both highly electronegative, so they would pool evenly. If you have carbon to hydrogen, that's nonpolar. Okay. So what is polar would be when you have one very electronegative and one very not electronegative in a bond. So nonpolar is a little more common, I suppose, just because there's a lot more ways to do it. All right, but here's the weird one explained on this slide is the carbon dioxide, so make sure you're clear on that one. All right, so here's water. Water is very polar because it is made up of polar covalent bonds, and the shape of the molecule is such that it has clearly defined areas of partial positive and partial negative. And then anything with carbon to hydrogen, any of these bonds would be nonpolar, so that give you a nonpolar example. And then carbon dioxide is the special case. All right, hydrogen bonds. Now hydrogen bonds, let's say you have one molecule, here's a water molecule, just like I said, all right, doing that V shape. And then you have, here's another water molecule. And then here you have another water molecule. If water molecules get close enough to each other, so typically when they're in the gas phase, they're too far from each other to do this. But when they're in liquid phase, the molecules are closer together. And what will happen is a very weak bond called a hydrogen bond will form. Hydrogen bond is a terrible name. I hate this name. I wish they hadn't called it this. Because, I'll tell you why. Because a hydrogen bond is not a bond between two hydrogens. It sounds like it would be, right? In fact, I'm going to put that on the test. True or false, a hydrogen bond is what we call a bond between two hydrogens, and you need to say false. Because a hydrogen bond is not a bond between two hydrogens. All right, so then what is it? Well, and you know, I didn't get to choose the name, so I'm sorry. Apologize for the name. What a hydrogen bond is a weak bond between the partial positive end of one molecule and the partial negative end of another molecule. So notice how this is arranged here. And the hydrogen bond is shown as a broken line because it's a weak bond. A covalent bond is drawn as a solid line because it's strong. The hydrogen bond is always drawn either as dots, like a dotted line, or on this picture a dashed line. But you have the weak bond between. Now remember, this hydrogen on this water molecule has a partial positive. Try to put it there. And this side of the water on this molecule down here has a partial negative. So it's a weak bond between the partial positive on one molecule and the partial negative, or the slight positive on one molecule and the slight negative on another molecule. dot, 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 dot. That's the attraction. Now, the thing about hydrogen bonds is they are very weak individually. All right? But this is important. Write this down. Hydrogen bonds are weak individually but strong collectively. So they create a strong force when there are a lot of them. So let's say you have a drop of water. Collectively means when you have a whole bunch. As a group, they are strong. So when you have, oh, I lost my mouse. Where'd I go? Collectively strong. That's what I'm trying to write. All right. So they're weak individually but strong collectively. So if you have a drop of water, you have gazillions, I don't know what the actual number would be, but you have gazillions of hydrogen bonds that are in place at any moment. Now, each hydrogen bond is formed and broken constantly. Well, different hydrogen bonds are formed and broken constantly. It's just like if I put a whole bunch of people in a room crowded together and everybody was moving around, like at a really packed party or something, and everybody, is moving around. Have you ever been somewhere where you were like literally you were touching people as you moved all the way through? You were touching different people, but you were constantly touching somebody as you moved through the crowd. It's like that. The water molecules are moving around each other, but they're constantly forming and breaking bonds, these kinds of bonds, these hydrogen bonds with other water molecules, such that at any fraction of a second, there's so many of them in that drop of water that it holds the drop of water together as a liquid. So it's really kind of interesting. Other liquids don't do this. So we're used to water. We don't think it's very interesting. And actually, chemically, it's very odd compared to a lot of other things that we can study chemically. And it's because of the shape of the molecule, because it has those partial positives and the partial negatives, that it can form these bonds in a way that a lot of other things, almost no other liquid can do what water is able to do because of this. It's really actually kind of interesting. All right, so each hydrogen bond is, and we write H bond because we're lazy. Each hydrogen bond is weak and short-lived, but lots of bonds together are strong. So I say weak individually, strong collectively. All right, they form and break continuously, but in any drop of water, you have a lot of them. At any fraction of a moment, you have enough of them in place that it holds everything together. All right, so the covalent bond that hold each molecule of water together is very strong, but the hydrogen bonds between the water molecules are weak, but collectively strong. So we have to talk about water, all right? We cannot imagine life without water. In fact, when we look for life on other planets, what we're usually looking for is evidence that there is water or there ever was water on the planet. That's how narrow our view of what is necessary I think it's kind of narrow, that we can't even imagine how life could exist without water, so we look for water or evidence that water once existed to look for evidence of life on other planets. I think we have to open our mind that maybe there's a way that life could exist in some other way, but it's not usually, if you read the literature, when they find evidence of life on other planets, that's what might come out in the news. What they really found was evidence that there could be water, or that there might have once been water. So it's kind of an interesting thing that we do. But water makes up a huge amount of everything in the living organism. Most of the cell is made of water. Most of what's outside of the cell is water. So you're just a big bag of water. And so it's just critical. And it comes down to the polar structure we just went over, that partial positive and partial negative thing. And the fact that because of that, it forms these hydrogen bonds that it constantly forms and breaks. Everything comes back down to those rules. You know, we talked a little bit about you're learning the fundamental rules. If you ever haven't, you know, how something interacts with water is always going to have to do with these just fundamental characteristics, the polar nature of the molecule and the forming and breaking of the hydrogen bonds. You probably know there's 3 states of water: liquid, gas, and solid. When you study this kind of science, you know that, you know, when something is in the gas form, it has more energy, more what we call entropy, more random, more space between the molecules. When the molecules come closer together, they have less energy. They can make and break bonds because they're just closer together. That forms the liquid. And then solid is when they stop, when the molecules don't move and they're close together and they don't move around each other anymore. That's a solid. So in water, it's usually what we call a crystal, which you would call ice. All right. And when water gets so cold that it makes ice, the hydrogen bonds whatever hydrogen bond was there when the molecule stopped moving becomes sort of held. But each molecule pushes out on the other molecules just a little bit. So what happens, I don't know if you've ever done this, but have you ever filled up a water bottle all the way to the stinking top and put a cap on it and put it in the freezer, like you were going to take it on a hike the next day, and you thought, oh, it'll melt while I'm hiking and then I'll have cold water to drink? It will bust that bottle apart every time. You can't fill the bottle to the top if you're going to put the cap on it and put it in the freezer, because when the molecules stop moving and they form their semi-permanent hydrogen bonds, they push away from each other a little bit, and the ice expands just a bit. No other liquid would do this. No other liquid would ever do that. It's the weirdest thing if you study enough chemistry, but that's what happens. And so the density of ice is less than the density of liquid water, and so ice floats. No other solid would float on top of its own liquid. Solids are supposed to be more dense than liquids. So if water followed the rules of most molecules, the ice would sink. But it doesn't, because of those hydrogen bonds kind of pushes on each other just a bit and expands the whole structure. So if you doubt me, get a plastic bottle of water, open it up, fill up the space so there's no extra space in it, put the cap on, put it in the freezer. It will bust open that plastic. My children, I told them this when they were kids, they kept doing this. I would buy them a $10 bottle, you know, like a plastic water bottle to take to school. They insisted on filling it all the way to the top, putting the cap in the freezer. The next day, Mom, my water bottle is broken. I explained to them, you know, son, you can't fill it all the way to the top because ice expands when it forms. The next day they did it again. I swear I spent $100 on water bottles. I don't know why they wouldn't believe me. So you know, it's unusual though that it does that. Now let's talk about heat capacity. We have a saying. I guess it's a watched pot never boils, which basically means if you stand there and watch a pot of water, it takes forever for it to start boiling. And it's kind of a reflection of how much energy you have to put into water to break the huge amount of hydrogen bonds that wouldn't be needed to start to convert that liquid water into gas. And the same thing with heat of vaporization, not just boiling the water, but then turning the water into steam. Again, a lot of energy to push it out into the gas phase. and it's only because of the huge amount of hydrogen bonds. The other liquids don't have this issue. Like if you heat, I don't know if I would recommend this, but I'll just tell you what would happen. If you take pure alcohol and put it in a pan and put it on the stove, it will boil very quickly. No, it will be completely different than what water would do. And it also, alcohol evaporates so quickly that you probably don't even need to heat it up too much, but it'll boil and then evaporate so quickly because alcohol doesn't, if it's pure alcohol, it doesn't form hydrogen bonds. It's not, the structure of it is not the same. But water is special, okay? And so it has a high heat capacity. Have you ever jumped into a swimming pool at the beginning of summer and it's still ice cold? Because the water is very slow to heat up and it's very slow to cool down. So in the spring, the air temperature might be 90 degrees in Texas, but it takes a long time. It'll be middle of July before that water temperature has really gotten up. And the same thing in the fall, though. The air temperature might change. You guys know how it is overnight. Suddenly it's very cold and you might see your pool steaming because it's still holding the temperature from August. So it's very slow to cool down. And it's because all those hydrogen bonds that have to be reformed or broken, it's just very slow to change temperature and to change phase. Now, the reason that we think of water as being the most important element of life, not only are we 60 to 70% water, but water is the solvent for all the chemical reactions that go on. So a solvent is the liquid portion of a chemical reaction. Most chemical reactions occur in liquid form, in liquids. The solute would be other things that are mixed into the liquid. And so an aqueous solution is just a mixture where water's the solvent. So in living organisms, water is the solvent for inside the cell, outside the cell. It's just the most, it's just the relevant solvent. And then the solutes will be the other reactants. Remember we talked about chemical reactions. The solutes can be the other substances, but all chemical reactions in biology take place in a liquid, in water. Inside the cell, maybe outside the cell, but in water. All right. So anything that is polar or fully charged mixes very well with water, and we call those things hydrophilic. In this case, hydro refers to water. Sometimes the root hydro refers to hydrogen, but in this case, hydro refers to water. And philic means the love of something. All right? Philic or phile, hydrophilic. So Philadelphia is the city of love. I don't know if you know that, but the Phila in Philadelphia. Now I've been to Philadelphia and I'm not sure, but that's where the name comes from. Okay? Philadelphia. Philadelphia. Try to think of another name. If you are let's see, trying to think, something else that has this phile, P-H-I-L-E. Well, you guys will think of something. It means love, the love of something. So anything that is hydrophilic, it means it mixes well with water. It likes water. So things that are fully ionic, fully charged, or things that are partially charged, polar, mix well with water. So we call them hydrophilic. Anything that's nonpolar is hydrophobic. So nonpolar things are hydrophobic. They don't mix that well with water. Now this says do not dissolve in water. Not well, not easily. So for example, oil is nonpolar. It doesn't mix with water. All right, so it's hydrophobic. So phobic, in this case, hydro again means referring to water, and then phobic is from the root meaning the fear of or dislike of. So hydrophilic and hydrophobic then becomes really critical to thinking about, we said water, liking water would be important to life because water is the solvent of life. So being able to understand that ions and polar molecules are going to mix well with water, but things that are nonpolar molecules will not mix well with water actually becomes critically important to what's going to happen inside the cell. So this chemistry is going to inform you. You'll be able to figure out what's going to be able to react and what's not going to be able to react, because some things won't mix with the water and some things will. There's all kinds of things that are going to be dependent on your ability to identify what's hydrophilic and what's hydrophobic, what's polar or ionic and what's nonpolar, because that's a big distinction. Okay, I'm going to take a break because I feel like I've been talking for a while, and I'll pick up with this continuation of this topic in the last lecture segment.